our time productively tomorrow morning for a review session for the exam, okay? There won't be prepared lecture of sorts. I'm really looking, to try to answer your questions, right? To try to clarify things. And so, again, the exam is closed book, and any information you need, I promise you'll have.
Does that include the accredited piece?
Yeah. All right, very good. We've been talking since the beginning about statics, and so we had, for example, in electrostatics, we have that the electric field inside a conductor is zero. Right? So if I have some conducting material, and for example, I put it between two capacitor plates, then what we know is that, the electric field will end up being perpendicular to the surface of the conductor, and the E field inside the conductor is zero. There'll be surface charges that are moved to the surface of the conductor in such a way that we cancel that, right? But since we've been talking about things like in magnetostatics, we had things like current, right? So I could have, some conductor, and I, put a battery across it, and there's going to be current that's flowing, right? There's current density in here. And there's something pushing those charges along. They're not, if we gave them a push and then there was no resistance, then they would just keep moving. But, there is resistance. It's futile, but we have no choice. And so there's clearly something pushing those charges along. There is, if we think about the force around this closed loop, it's not zero. So right? And if this was just electrostatics, then the force is just the charge times whatever the electric field is, and this F dot dl around that closed loop would be zero. So there is, something going on here beyond electrostatic field that's pushing that. And so we want to start talking about that and remind ourselves of life beyond electrostatics. We've talked about magnetostatics, but there's still something more here that's going on, okay? So let's talk a little bit about some model of current in a conductor, okay? So let's talk about a simple model of current flowing in a conductor. And start with the simplest possible model, and we're actually going to end there too, because I'm not going to talk about condensed matter physics. And let's just think of what's called the Drude model, okay? So the Drude model is one where we think about we have a free, the conduction electrons are thought of as a free gas, okay? So we have a free gas of conduction electrons. All right. And if there's some force acting on them, then we can think about, you know, the force on a given electron, in this case, say due to an electric field, would be E times the charge of electrons to the electric field, and that would cause the electrons to accelerate in the gas. So there's some electric field that is coming from this battery, and the electric field is pushing electrons along. Now, if I have a current density, and I think about this in steady state, this is constant. And of course, the current density will depend on the density of electrons. Let's call that density little n, and then the charge per electron is minus E. So this is the charge density of the gas. And then there's some velocity in which they're moving, okay? Now that velocity is in general going to be fluctuating in some way because of thermal fluctuations. And let's just think about not the fluctuating part of current, but the mean current. So I'll just think about the average over a thermal distribution. Okay? So that's a current density thought of this. Now if this says that this is changing with time, that would cause this thing to keep accelerating the current. It comes to steady state because of resistance, okay? And the resistance is happening because it's not, I mean, if there was a perfect superconductor, when you put this filter, we'd have infinite current across it, and that would be bad. But we know, we can think about this where we have a free gas of electrons that are, sort of, they would want to move in some direction given an electric field. Of course, there's some fluctuations there. But there's also, in addition to the Drude model, in addition to there being a free gas, we imagine that there are defects in the perfect lattice within which the electrons are flowing that they will scatter off of, okay? So in the Drude model, we think about, there are defects sort of somewhere. And these will just scatter in some way. There's still a force on them. And so there's an average velocity, which we call the drift velocity, okay? So they're going to try, because there's a constant force on them, the force is trying to accelerate them, but there's drag. I mean, life's a drag, and you can't help it. And so, there'll be a drag on force on this system, which will cause, which will damp out the motion. So in addition to this, there's a damping force, which we'll just say has a drag coefficient, a rate which is related to the rate of collisions. Times the velocity, okay? And it's only the mean, so this velocity is what we call the drift velocity. And when we apply this force through the electric field, there'll be, cause it to accelerate, and there'll be a drag force. Okay, that's a simple mechanical picture of the flow of current in the Newton model. Okay, so with this said, we have an equation of motion for the current density. Because if I multiply this by the charge density, that's the current density. Okay, so this tells me that the current density, which is equal to minus the electron charge times the density of electrons times the rate of change of the drift velocity. If I divide by the mass of the electron here, then what I get is that this is equal to minus E over M, or plus, I have to multiply it by minus E, so E squared times the density of the electric field, and then minus, let's see, yeah, current, yeah. Okay. Or written slightly differently, something I'll call the plasma frequency. Oh, I forgot to divide. Yeah, no, this is right. The plasma frequency. Let's see, I'm getting my factors right. Excuse me. I'm so confused here. Yeah, I think that's right. Okay. No, the mass is here. I'll define the plasma frequency in a moment. So this is the plasma frequency over 4 pi times E, where the square of the plasma frequency is equal to, according to this expression over here, it's equal to 4 pi times the density of the electrons times the square of the electron charge divided by the mass of the electron. Okay? That's just a definition. That comes from, guess what? Plasma physics. And plasma is a gas of charged particles. Okay? So this, in the Drude model, is the simple equation of motion for how current flows in a finite a material with a finite amount of conductivity that's determined, and the amount of conductivity depends on this rate of collisions, the drag force. And this equation actually is known as Ohm's law. It's not the familiar form of Ohm's law, but we'll reduce it to that in a moment. V equals IR. That doesn't look like V equals IR, but it actually is in a certain limit, okay? So in particular, in steady state, there's a steady current, okay? So after the transients die down, the transient, by the way, this has the units of, that's the plasma frequency. Yeah, no, that's right. Yeah, so this, I just wanted to check the units in my head, and right, yeah, okay. So let's look at the steady state solution, and we'll check the units, because then I know I've done it right, at least I've got the units right. Okay, so in steady state, the current is no longer changing. So we can set it equal to 0, and in steady state, we get this equation, that the current is proportional to the electric field, and the proportionality constant we call the conductivity. So this is, in some sense, the DC version of Ohm's law. Does this have the right units? Well, let's think about this. This is a frequency divided by a rate, which is a rate. Okay, so this has the units of 1 over time. What are the units of electric field? Charge squared over, charge over distance squared, right? So the units of J are current per unit area, and current per unit area is charge per unit time per unit length squared, right? That's current density. The units of electric field are charge over distance squared.
Times 1 over t.
And then if we multiply that by 1 over t, ta-da, got the units right. Okay, at least there's that. Okay. With epsilon and that, you never know. All right. So, very good. So this is Ohm's law, and in particular, if we look at a simple example where we just said, let's say I have, a little resistor here. We'll put this battery here between it. There's some distance between these two parts of the battery, and it has a cross-sectional area A. Then the current density is the current per unit area. And if there is a voltage across this resistor, what is the electric field that is along that resistor? We're so screwed up with Green's functions that we don't know how to do this anymore. If I have a voltage across a distance and it's a constant, what is the electric field? V over D, right? It's the gradient of the thing. Yeah?
You're saying the electric field was constant or the voltage was constant?
Well, I'm saying the fact that it's kind of a uniform field across this.
Okay.
Right? This is simple expression. So if I plug that into Ohm's law, it says that I over A is equal to the conductivity times V over D. Okay? Which tells me that the voltage across that resistor is equal to I times the resistance, where the resistance is equal to what? It's equal to D over A times 1 over the conductivity. Okay? So that's the familiar form of Ohm's law from high school. And we've made it more sophisticato, but this is a specific example of it, right? Now here's something crazy, actually worth thinking about. Firstly, what are the units of the conductivity in CGS?
1 over t, you said?
It's 1 over, we can see that, it's a rate. And that makes sense physically because it's related to the rate at which there are collisions. So it's a characteristic of how often you have collisions. That's what really the conductivity is physically. It's about the finite. Now, resistance is a bulk property. It's not a property of just the material itself, but the geometry. Okay, so it has things like how thick is this resistor and how long is that resistor. But just out of curiosity, what are the units of resistance in CGS? So we got 1 over time. So the units of resistance here are 1 over time. And then we got length of a length, which is equal to 1 over a velocity. That's kind of interesting. I mean, it's we used to think about ohms, and we should. I mean, you work in the lab, don't write your resistance in. But if you had to guess, there's something known as the impedance of free space, okay? Which is a thing we'll talk about. Impedance is resistance, okay? And so impedance of free space is a property of free space. In CGS units, what would you guess the impedance of free space is?
125.
What's that?
125.
Well, there is something in there's 377 ohms is in MKS is what there is this. But what we know is that resistance has the units of 1/velocity, and there is. If it's the resistance of free space and there's nothing else in the problem that tells me anything else, what velocity is there? C. The velocity of free space is 1/c. That's what it is. It has nothing to do with 377 ohms. What the heck is that? Yeah. Anyway, it's free space. There's only one constant in the world in EM, and it's C. That's why we love CGS. Okay. All right. All right. I heart CGS. Yeah, go on.
So the impedance of free space is entirely real, there's no complex component to it?
That's right. I mean, the impedance of free space is real. There's no, I mean, we'll talk a little bit about that kind of stuff soon. Yeah. Okay, but I digress. Right, okay, so, there's things to do. All right, very good. So, all right, so because of the fact that this thing is colliding, it means that energy is being dissipated, right? So, you know, you're applying a forces thing, you're trying to do work on these charges and give them energy, and that energy is being taken away through these collisions. So at some point it reaches steady state, and the work you put in equals the dissipated energy that comes out, okay? So when we have with resistance comes ohmic heating. So let's think about the rate at which we're doing work on the system. So the force that is being applied to each electron, well, it's the Lorentz force. This is whatever force there is. There may be magnetic fields as well. So the rate at which the battery does work on the current or the charges is equal to that, just for mechanics, right? If I move through a distance, the work is dl, the rate of work is dl dt, okay? And so that's equal to the sum over all the charges, q sub I, v sub I, that E, which I could also think about as this is related to the current density. If I write Q as a sum over delta functions, then I get this expression, okay? So J dot E here is what we call, is the rate of ohmic heating per unit volume, okay? that's how much power is being dissipated by the resistor in this context, okay? Because it has to be dissipated in this steady state in the sense that it's in steady state. There's no more energy going in, the energy in is coming out. All right. And this, of course, if we thought about this simple model, again, this is equal to the current flowing times the voltage across it for this simple model, which is I squared R, another thing we know from high school physics, right? It's the same, that's how much power is being dissipated in the resistor. Okay. All right, very good. Now, again, I'm coming back to what is on this board over here. If this energy is being dissipated, the energy that's being dissipated is the work that the battery did, or something did, right? And so what we know is that there is work done to push the current around the loop. And we defined what's known as the electromotive force, which is not a force at all. It's a force per unit charge. And it's typically written as script E, as the work done per unit charge around the closed loop. The electromagnetic force, what it's the force per unit charge, which has units of electrostatic potential. Or voltage. So while it's called electromagnetic electromotive force, it's the force per unit charge, right? Charge times voltage. Yep.
Is it force per unit charge? Because we have the multiplier of DL, right? So we have force per unit charge times what?
Yeah, I'm sorry. This is the but it's the yeah, you're right. It's the energy per unit in the, you're right now. Thanks for that confusion. All right, so what can be the source of an EMF? What can do this?
Battery.
Well, battery is one example. And how the heck does that work? Well, if I think about a battery, you know, I have, kind of draw it like this. I have an anode and a cathode here. Okay, so let's say that this is, let's call this the anode and this the cathode. And then I have, you know, a resistor, and there's current flowing around here, okay? Now, how in the world is this happening? It's not due to electrostatics, because we know if this was just Q times E, what's happening in this situation is there's electrochemistry. And so somehow there's some, you know, solutioning here, which there are some positive ions that are flowing against their better interest uphill. And they're doing so because somehow they're being dragged to this through the electrostatic chemistry inside here from the anode to the cathode, there is an electric field, but yet the ions are going in this direction. There's a current flowing against the electric field. So J dot E is less than 0, which means that instead of heating, I'm creating energy, right? So when J dot E is negative, we have created electromagnetic potential energy, which is what drives the current. And this electrochemistry cannot be understood from classical electrostatics. There's some other force that's somehow causing this ion to want to go uphill because somehow it's in its interest to do so. There is forces that are related to the way in which the energy levels of the ions make it better for them to go up this hill and then lose this energy. Okay? Here's another example. The old Van de Graaff generator. If I had hair, it would stand up. Remember what a Van de Graaff generator is?
Oh, yeah.
Everyone loves that. So you got this like bulb-like thing, and you got a belt, and I got, a handle, and I can turn the crank and make this belt go, and then there's these brushes that are the belt, and it's like, get your sister and zap her because my sister was too old for me. She did that to me. Because of the fact that you have these two different materials, you can strip the charges off. So you have these electrostatic charges that, basically the positive charges move up the belt, and then this is negatively charged. And, then I can connect this through a resistor or through, something through the air that's basically like resistance, and current flows this way. But all the positive charge, this is more positively charged, more negatively charged. There's an electric field from these charges going in that direction for positive charge, but I'm moving the current. But just this force of energy, just the mechanical energy, I'm pushing the electrons uphill. And by doing so, I've made an EMF. So that's another example of something that's not electrostatic. It's just you're just taking the electron, picking it up, and pushing it uphill. Okay? Okay, let's talk about another example, what I'll call motional EMF. Okay, so here let's think about the following example. Suppose I have set up between somehow maybe some permanent magnets, a region with a very uniform magnetic field. Uniform magnetic field, uniform magnetic field. We decided to make this rectangle this big, but anyway. Yep, so this is the B field. I have it into the board, and it's uniform in this region. And now let's say I have a loop of a circuit, and I'm going to pull on it. I'm going to pull on it with a certain velocity to start, okay? And as I pull on it, of course, there is a velocity that this thing is moving with. And so there's going to be a Lorentz force acting on the electrons, right? The Lorentz force acting on these electrons, as they call it the magnetic force, is equal to whatever, let's say they have some charge Q, it's the electron minus E, this velocity I'm pulling on it, cross B. And what direction is that force in?
It's,
V cross B, my thumb, V cross B. So the force is like this, right? V cross B, like that. All right, so there's going to be a force that's going to push the charges along this loop, okay? And then they'll keep going, and then they'll come around, but then there's a force, right? Of course, as this current starts flowing, then because it's flowing in this direction, there's another force acting on this whole thing. What direction is that force acting in? V cross B, this way. So if I'm going to pull it, there's resistance now, but the resistance is coming from the fact that this thing there's flowing current, and the flowing current in the thing gets another magnetic force. V cross B gives me that, okay? So there's the force on it due to the fact that I'm moving this thing, and then once the current starts flowing, so I can just say I'm pulling equal and opposite to that force so I don't accelerate the thing, okay? So as I try to pull this thing, there's an equal and opposite reaction, the back reaction force, which pulls against me. I'm going to make these guys equal so that I do this at a constant velocity. All right? So let's calculate what the EMF is in this situation. Because if there is a current flowing around this loop, there is an electromotive force, and that electromotive force is coming from in this frame of reference, the lab frame, also known as the classroom frame, is where we're seeing this moving loop, right? So the EMF over here around this closed loop, okay? Yeah?
Are we saying in this wire that we're pulling there's only electrons?
Well, there's whatever is free to flow, and typically that's the electrons.
But if there were protons also that were stationary, wouldn't there still be a force on them too? They just wouldn't move, the whole object would be?
But they're fixed, they're unable to flow. Only the electrons are free to flow. There'll be a force on them, but there'll be an equal opposite force on them, and there'll be no flow. It's only the conduction current that can actually move in this direction.
So the E field goes down then, because it's cross, V cross B? Or?
There is no electric field in this in this frame of reference. Okay? There's only a magnetic field, of course. We'll come back to that point in a moment. Okay, so what is the EMF here in this case? Well, it's equal to, there's the force going in this direction. This, we imagine, the electrons can't go anywhere. They're held in the crystal, so there's equal and opposite force. The only force that exists is in this leg of the problem. So that's equal to 1 over Q times Q V over C times B times this length. We'll call this the height of that H. Okay? Now, what is V? V is the speed at which I'm moving. If I call this distance from here to here S, then V is equal to minus ds dt, because I'm moving it in this direction. okay? So this then is equal to 1 over C minus sign ds dt h times d, which is equal to minus 1 over C d by dt, because B is constant in this case, d times s times h. Okay? But what this is equal to is the flux of the magnetic field through this closed loop, right? So the flux through that loop, if I'm going this direction, okay, this is the area. It's all self-consistent. If this is the contour integral, then that's the direction of the normal into the board. That's why I do it that way. And this we'll call capital phi, not to be confused with the electrostatic potential. Okay? This is the flux of B through the surface, enclosed by this loop, by the usual rules. And so what we see here is that the EMF is equal to minus 1 over C, the rate of change of the magnetic flux. Let me call it phi sub B, just to emphasize that fact that this is the flux of the magnetic field. Okay? And that is this minus sign here is what is sometimes known as Lenz's law. And that is to say that, and that's this reaction force, that if the EMF that is induced in such a way to try to not have the flux change, right? Because this current loop will create its own magnetic field. And in what direction is that magnetic field? The opposite, right? So it tries to oppose, so an EMF is induced to oppose the changing magnetic flux.
Is that like the chemical battery, or there's like a Lenz's law for it?
That's a different, it's also true, there has to be something that's creating energy. There's current going against an electric field. That's always what creates energy, because J dot E dissipates energy, and minus J dot E creates less magnetic energy. But the source of it is quite different. This source is really due to quantum mechanics and the notion of energy levels in ionic junk versus this, which is just Lenz's law, and which is just Lorentz force law. Okay, we derived this here for the specific example, but this is generic. This is general. So the motional EMF is general. So let's imagine a more generic situation. Let's say I have some loop with some orientation that I've chosen for it. Okay, so there's some contour. I can think about this as a physical loop of wire, but in a moment we won't. Okay? And it's moving through some non-uniform magnetic field. This magnetic field was not uniform because it ended abruptly. Okay? That was important for this. Otherwise, I would have an equal and opposite force on both sides and no current would flow. It's the fact that only one part of the circuit was bathed in this that the current was able to flow at all. So here's some magnetic field. And now let's imagine this loop is moving. And so now here's the loop at some later time. It's in a different magnetic field because the magnetic field is not homogeneous. Okay? So this is the current, this is the loop at, I didn't want it to, it's supposed to be exactly the same shape. Excuse my, all right, it's not that it stretched, it just looks like it stretched because I'm not very good on this. Okay? So this is at some time t, and this is some, say it's some differential time dt because the thing is moving. Okay? So there's some, this thing is moving with some velocity in some time dt, and that's the sort of height of this little cylinder. Okay? So this, the combination of the bottom and the top and the ribbon is a closed surface, okay? And so I can think about the whole surface, right? It's this whole thingamaboozy. Oh, God.
One of those peanuts you wash your car with.
That's my closed surface, okay? And I want to look at what is the magnetic field, the total flux of the magnetic field, where the normal is now out of this surface. And I ask you, what is this? What is the flux of the magnetic field through the closed surface? Zero. Because that's what we know from Maxwell's equations, the flux of the magnetic field through a closed surface. There's no magnetic monopole, so this is zero. But this is equal to the sum of the fluxes through the top, the bottom, and so if from this orientation, this is the normal, and this is the normal, but that's the opposite to the normal to the other flux. So what this is equal to, let's make sure I get the signs right here. Right.
It's like the KVL for magnetics. So it equals to zero. The sum is going in equals the sum going out.
I think there are lots of things, yeah, I mean, it's true. There are things of detailed balance where things go in and things go out and they balance. But I would just say, this is just this fact that the flux of the magnetic field through any closed surface is zero. That we can then break this up into the different pieces, which is the flux of magnetic field at this time, that's the top, right? The bottom, it's in the other direction because of the way we've chosen things. So that's the top. This is the bottom. And then we have the dA here, and if this is dL, a little loop of current, then dA is equal to the cross, but with the n hat out of it, d is d cross dl, dt cross dl. Dotted into the magnetic field. Okay? And then I do the contour integral. So that's the sides. Okay? This is the little surface area pointing with the normal, right? And then we can play the rule of switching the cross product and the dot product on this thing and write this as B cross, or B cross B dotted into the F. Okay. So, and then I have the dt. So if I then subtract that around, what I find is that the integral of v cross b dot dl around the closed contour is equal to minus the rate of change of the flux of the magnetic field through the contour. Which is what we had for this specific example, but now it really has nothing to do with that specific example. It's a general rule, okay? Yeah?
And this is related to the EMF through capital phi?
Well, this is, so this is the only, the EMF is coming from the Lorentz force. That's how we showed it here, but here we see that exactly. And in fact, if I write this as like that, then this is the EMF. But the EMF is coming from the point of view of the lab frame at the Lorentz force acting on the charges in this loop that causes them to run around because of the V cross B force. However, we know in physics that we must be the case that the physics is the same in all reference frames that are inertial, okay? And we already see a hint that there was something hinky going on with the Lorentz force law. Because the Lorentz force law has a V in it. But whose reference frame am I in when I talk about V? In whatever frame I'm in, right? So, if physics is the same in all inertial reference frames, then in the rest frame, of the moving, of the co-moving, I'll call it, loop, there must be a force on the electrons. Because if there's a force on it in the lab frame, there has to be a force on it also in the co-moving frame. But in the co-moving frame, what is the velocity of the charges? 0. So where the hell is this force coming from?
E field?
An E field. So what this means is that the B field in the lab frame is an electric field in the co-moving frame. So in the co-moving frame, there's an electric field. And that has to equal so that means that what we're seeing, what's happening in the frame of the moving loop is that it's seeing an electric field. That electric field is not an electrostatic field. It's a field that's coming from the fact that in its frame, the magnetic field is changing in time. And so what we've learned is that a magnetic field changing in time creates an electric field in some reference frame. Now, I should say that this expression for the magnetic, the co-moving, if I wrote this, the E field in the co-moving frame is equal to this, is only approximately true because we've used Galilean transformations. Galilean, non-relativistic. That doesn't change anything about this derivation other than to interpret it as this E field is not exactly correct because of time dilation and length contraction, which we'll talk about more. So the exact expression here will have a relativistic gamma in it. We'll come back to that at the end of the semester. Okay? But that's sort of neither here nor there. What we have is, in this case, though, we solve this problem by thinking about a fixed magnetic field that's fixed in time in the lab frame as a constant but non-uniform and moving relative to that. We could have done the complete opposite and kept this fixed and changed the magnetic field with time. And that's the universal law of Faraday. And Faraday just did this experimentally. He took some loop current and he shoved some magnets in it, and he saw what was going on and saw this relationship between changing magnetic fields, EMF, and then thus electric fields. So the universal law of induction, which is Faraday's law, says the following: in a given reference frame, the EMF is equal to what this is, which is equal to minus 1 over C d by dt of the flux of the magnetic field through the surface enclosed by the loop. Okay? And if I have a fixed loop, then this is equal to this. Is that clear? Right. So that's Faraday's law. Faraday's law tells me that the circulation integral of the electric field is not generally zero. In electrostatics, it's zero. But if I have a changing magnetic field, then I can have an EMF. I can have a circuit. Yeah. Yeah,
The comment about C being fixed in space is just so we can move the derivative instead of.
that's correct. And make it a part of the derivative. Otherwise, we have this other stuff, right? The ribbon and all of that. And of course, we can use Stokes' theorem to relate the contour integral to a flux integral of the curl. So what that tells us is that the differential form of Faraday's law is that the curl of E is not generally zero, but is equal to the local rate of change of the magnetic field. Okay? So in electrostatics, the curl of E was zero, but generally it's not if the magnetic field is changing locally. And that's related to the fact that in a co-moving frame, so this really shouldn't think about electric and magnetic field as separate things. They are the same thing seen in different reference frames. Which is why they should have the same units, right? And do they? Del has the units of 1 over length, yep. And this has the units of 1 over length. Good, all right. All right, finally, I want to talk about, we talked about the work we did to create a charge distribution, and we ultimately thought about that as, we could think about the work that we did as having been energy stored somewhere, and that energy was stored in the electric field, okay? So recall in electrostatics, the work done to assemble a charge distribution, rho, was equal to the potential energy stored in the system. And we can think about that potential energy as being stored in the electric field, okay? Where the square of the field is the energy density, okay? I want to now ask about the work done to create a current distribution. Why is there work done? Well, because if I start with nothing and try to push things around to create current, there's going to be a back EMF on me. Because when I start pushing current around, I'm going to start changing flux, and that ain't good. The thing doesn't want its flux changing, and so it tries to create the back reaction. That's how regenerative braking works in your Prius, by the way, if you have one, right? I mean, you are basically using the back EMF. The work done to regenerate doesn't come for free. The kinetic energy in your car is used to generate power back into your battery. It slows the car down, and that kinetic energy goes back into your battery. That's back EMF. Okay. Maybe I'm not one who drives a Prius, but anyway. I'm not kind of. All right. So let's think about this, and let's calculate this. So let's do it just as simple, the simplest kind of picture. Let's imagine I have some little sort of differential part of my current density, and there's I have some current, and I want to ask how much work does it take for me to take I to I plus VI? I'm going to try to push around more current. As I try to push around more current, there's going to be a back EMF, okay? And I'm going to have to do work against that back EMF. So there's, there's a magnetic field here at this given I, and then B is going to go to B plus delta B. And I want to know how much work that I did. Or let's put it this way, what's the power, the rate at which I have to put energy into the system. So let's look at the rate of change of a little change of how much work I had to do to take the current and make it go up by this amount, okay? All right, let me remind myself of something. Right, okay, so the work I do is, as we just said, this is the work I do is going into creating electromagnetic energy. And we said that the rate at which energy is created is minus J dot E, because J dot E is the rate at which energy is dissipated. So this is going to be equal to the, whatever, there's a certain current density. This little circle here is a little cross-sectional area I'll call little dA. So I is equal to J little dA. Not to be confused with the dA, which is in that surface area, right? This is the cross-section of a little piece of the current density, okay? So J dot dA, J dot, so I'm going, as I increase the current, I'm going to have a EMF induced, and the EMF is related to the increase in the flux, and it goes in the opposite direction, right? So my delta E is going to try to oppose this change in flux, and it's going to go up against the current. So there's an additional electric field that I will be generating according to Faraday's law as I try to crank up the current. And that delta E will go according to Lenz's law to try to stop this increase in the flux. Okay. All right, so that's by definition what we mean by the work done. The work we're doing is by trying to push the additional current against the back EMF. That's the work I do, okay? It's different than we had electrostatics. There we started with charges and we moved, it was the Coulomb force that we were pushing against. Here the force we're pushing against is again against an electric field, but that electric field that we're pushing against is not an electrostatic electric field, it's the electric field coming from the changing magnetic field, okay? So that's why we had to go to Faraday's law before we could talk about the energy stored in the magnetic field. All right, so now we have to integrate over all space, and this is equal to this little dA and a little dL across. That's where the current is. It's in this little thing. There's a dA and there's a dL. Here's a chunk of this thing. We'll lose it. And so I can rewrite this then as minus J times dA, the cross-sectional area of that thingamabobby. And then I have, that's the cross-sectional area, and then I'm going around the whole loop, delta E dot L. So A dL over here, and that's where that came from. Okay. Right. Okay, now we've got Faraday's law. And Faraday's law tells me that this thing is minus 1 over C, the rate of change of I have a small electromagnetic field dotted into EA. Okay, so if I'm creating an electric field around this thing, it's coming from the fact that as I crank up the current, I'm increasing the flux. And Lenz's law says, put a back EMF to try to oppose that, which is this.
That's like, in those generators, they have that, back EMF.
Yeah, that's how a generator works. You're turning mechanical energy into electrical energy through the back EMF. All right, so let's put it all together. And we get 1 over C, the minus signs cancel. The integral over the little cross-sectional area there. I get J, and then the integral of d by dt delta B dot dA. Okay. So with that, I can think about how much work I did by trying to crank up the current by this amount. It's equal to, the minus signs cancel, I already did that, it's 1 over C, the integral dA, dL, I don't know where I already changed the L to dA. Yeah, there's too many of these things. The J delta D dot dA. Okay. So this I'm going to write as the integral of the curl of the vector potential dot dA. Because the magnetic field is the curl of the vector potential. But by Stokes' theorem, the flux integral of the curl is equal to the circulation integral of the field. That's Stokes' theorem. Okay? So when I put that all together, if I take this together with this, what I get is the dA, dL, we said was d cubed x. This is then equal to 1 over c, d cubed x, j dot delta A. And that's delta delta. Okay. This is close. It's not quite a cigar yet. This is analogous to the energy is the charge times the voltage, which is charge times potential. Here we have the energy is current per C times vector potential. It's the same thing that we had in electrostatics, but now in a magnetic kind of way, right? Charge times potential was energy. That's good enough earlier with the force and the length, right? Okay, now let's finally think about this in terms of the magnetic field. So we know from Ampere's law that the curl of B is equal to J times 4 pi over C. Which means that J over C is equal to 1 over 4 pi, the curl of B. So that tells me that the small amount of work I did by trying to crank up the current is equal to 1/4 pi, the integral over the current distribution, which, no, I'm sorry, is curl of B dotted into the change in the vector potential. Just substituting in that J is always related to the local curl of B. And now I can do integration by parts and write this as the derivation of this is damn complicated and it's not that important. The final answer and the concepts are. So now what I can just do an integral of this thing where I take the work from doing nothing to some final and write this as 1/2 the square of that. Right, that's say delta V squared is 2B dot delta V. Okay, that's where the half came from. And I just, so that's how I got this. Okay? The bottom line is this. It really is the bottom line. Okay. What we have shown through this, all these machinations, oh God, is that when we take current from nothing and we ramp it up to some final steady state current, the work we did against the back EMF is equal to this integral, which we can think about as the integral over an energy density, so that V squared over 8 pi is the energy density stored in the electric field, magnetic field. Exactly analogous to what we had in electrostatics. We thought that the work came from conservation memory, how much work I had to do to push things around. At the end of the day, where did that energy go? The energy can be thought about as being stored in the field. In the same way, if I, drag my body up on the luge and I'm at the 10,000 feet, I spent a lot of work to do that. Where did that energy go? Well, some of it was dissipated because I was hungry, but some of it was still up there, and if I could just roll down the hill, I would roll. But where is that energy? It was stored in the gravitational field, and then the gravitational field gave it back to me and caused me to roll back the thing. The same idea here. The work I did to push against the back EMF is stored in the magnetic field. And this is the energy density of the field. It's B squared divided by, or 1/2 mu naught, if you care, if you still care to do so. All right? Whew.